So hello everyone, I am going to present a way to sum up squares and cubes, hopefully in a beautiful way. I mean, my talk has the word beautiful in it. Now I know that beauty is in the eye of the beholder, as they say, so maybe what I'm going to present that for me is beautiful, maybe you'll hate it. But I hope not, okay? So this what I'm going to do is really simple, at least in front of you. I mean, if I consider you as the audience, what I'm going to do is very simple. It is basically A-level mathematics, which is getting the sum of the squares, the formula for the sum of the squares, and the formula for the sum of the cubes. Okay, but when I teach this at junior college, the proofs that I was presented in the textbook, I didn't like them. Basically, they were a form of, some sort of telescoping sum. Some people call it the method of differences. And basically, I didn't like it. So I tried to look for alternative proofs that are a little bit more interesting. So before summing the squares and the cubes, I need to start first from summing the numbers themselves, the powers of 1. And I'm going to quickly prove it. I'm sure you have seen this proof somewhere, but I'm going to repeat it, okay? Basically, I have the numbers 1, 2, 3, 4, up to n, and I want to sum them up. And the idea is to rewrite them, but in reverse, underneath. Of course, the sum of the first row is the same as the sum of the second row. But if I sum them up like this, I get n plus 1 n times, in fact. Which means that twice the sum of the numbers is n times n plus 1. That's it. Easy. Okay? Basically, this proves that 2 sigma n is n plus 1, which usually is written as sigma n is n plus 1 on 2, as you know. Now, let's go to the sum of squares. And I'm going to do something similar. That's why I started with this, okay? So, instead of writing this as a row, I'm going to write a triangle of numbers. I hope it fits. So, 1, 2, 2, 3, 3, 3, 4, 4, 4, 4, and so on until a row of n's. So n, n, n. At the bottom, I have n n's. Okay? So let's think about summing this thing here. So if I sum this one, I can say I have a 1, obviously, and then I have 2 2's, which is 2 times 2, so that's the square of 2. And then I have 3 3's, which is the square of 3, 4 4's, which is the square of 4, and so on. So obviously, if I sum up these numbers, I get sigma n squared, right? So that's sigma n squared, great. But it doesn't tell me anything about how to find a formula for sigma n squared. Now, the trick is the following, and when I saw this, I said, wow, I've never seen this before. The trick is to rotate this triangle. So basically, I'm going to rotate this triangle. I'm going to rewrite it like this. I hope it fits. So n, 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 n. And then I have, so basically I'm rotating it like this, right? So this goes here. Then I have an n minus 1, n minus 1, up to n minus 1. Then I have n minus 2, n minus 2, up to n minus 2. And so on until here I have a 1, right? So I get something like this. If I rotate by, I don't know, 120 degrees, I think it's 120 degrees, I'm not sure. But anyway, so basically this goes here. This one that was at the penultimate row goes here, and then the 1, and so on, the 1 goes here. So the 1 goes here, here I have 2 2's, 3 3's, and so on. Now, obviously, this has still the same sum, because it's still the same numbers, okay? So that's also sigma n squared, and now I repeat the same rotation one other time, and I get this, n, 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 up to n, n minus 1, n minus 1, n minus 1, up to n minus 1, n minus 2, n minus 2, up to n minus 2, and so on until 1. So that's a 2. That's supposed to be a 2. And again, this has, the sum is sigma n squared. And then what you do is, I think some of you are noticing what's going to happen now. Basically, you sum up these together. And when you do that, you get 2n plus 1 all the time. And when I saw this, I said, wow. So 2 plus n minus 1 plus n is 2n plus 1. I don't know, 4 plus n minus 2 plus, I don't know what I have here, will be 2n plus 1. So we get 2n plus 1 everywhere. But of course, if I sum up these three, I get 3 times the sum of the squares. So 3 times the sum of the squares is 2n plus 1. Times what? Well, times how many values I have in this triangle. Which is what? It's that one, the one I started with. Because I have 1 plus 2 plus 3 plus 4 up to plus n values. Sigma n. And then you rearrange that and you get the formula for the sum of the squares. And this is what I've been teaching for the past 2 years or so to my JC students, because I find this to be much prettier than the, in my opinion, boring proof that is in the textbook. Anyway, so that's the sum of squares. Now what about the sum of cubes? Do I have enough space for the sum of cubes? Maybe if I delete this and I put it here, I do. So 3 times sigma n squared is 2n plus 1 sigma n. Okay? So sum of cubes. Now this one, I'm trying to remember who taught this to me. I believe it was Tony Gardiner, I think is his name. There was a time here where there used to be the math circle, and I believe Tony Gardiner came here in Malta, and I attended his talk, and during the talk he presented this proof, and it was so beautiful that I remembered it, and now I'm going to present it to you, basically, okay? So the proof is this. Remember, I need to sum the cubes. Okay, so we do this. We start with the numbers 1, 2, 3, 4, up to n, which is the same as what we started originally. And then we double these, 2, 4, 6, 8, up to 2n. This is quite annoying, but whatever. And then we have 3, 6, 9, 12, up to 3n. And then I continue this until I reach the nth row, which will have n, 2n, 3n, 4n, up to n squared. So we start with a square this time. So there we started with a line, then we ended up with triangles, and then we have a square. Okay? Right. This reminds me as well of when I was young, primary school, we had a chart and we used to say the tables, you know, the table of 2, table of 3. I was very, very young back then. It didn't go up to n, it went up to 10 at that point in time, but it's basically the same thing, okay? If you imagine n is 10, it's exactly the same chart. Now, let's sum this up. Now, first of all, I don't think that it's obvious that the sum of this is the sum of cubes, or at least it's not as obvious as before, but it is the sum of cubes. But it's not that obvious. So let's start by summing it up in the maybe naive way by summing up row by row, or column by column, which are identical in this case. Right, so if I sum up the first row, I get exactly the sum I started with, so that's sigma n. This is twice sigma n, of course, that's 3 times sigma n, that's n times sigma n. So here, this is, if I sum it up, I have sigma n. That's 2 sigma n, that's 3 sigma n, that's n sigma n. And then if I sum up these, I get sigma n. So the sum of these is sigma n squared. And this is, by the way, not just a proof for the sum of cubes. It's also a proof that the sum of cubes is the square of the sum of numbers. Because summing it up like this is the square of the sum of numbers. Okay? Now, I want to show you that this is actually the sum of cubes. How do we do this? I'm going to sum it up like this. Well, not me, Tony Gardiner did, but okay, I'm just repeating what Tony Gardiner said. Okay? So if we sum it up like this, then each of those is a cube. Now, this one is obvious. 2 plus 2 plus 4 is 8, which is 2 cubed. 3 plus 6 plus 9 plus 6 plus 3 is 27. You can take my word for it, okay? That's 3 cubed. Well, maybe you'd say, but that's a coincidence, right? It cannot be true for all of these, but it is. And the way to show it is to do this one. And if I get that the sum of those is n cubed, then of course for the others it's n minus 1 cubed, and I'm done. Okay, so I'm going to just sum up this one. Okay, and to sum up this one, really, it's about redoing almost this thing, because if I sum up only this, it is n sigma n, right? If I sum up only this column, or only this row, same thing, right? So we have n sigma n, and then if I sum up this part and exclude the n squared, because I don't want to add n squared twice, I get, well, this time I'm summing from 1 to n minus 1. So that is n, so here I think I need to write down the limits, right? I need to write down the limits, or else I can do this, so that I don't write the limits, okay? I sum it up twice and then remove 1 n squared, right? And I hope that that's an n cubed. Well, I need to use that formula. So this is 2n sigma n minus n squared. But there I said that 2 sigma n is n plus 1. So this is 2n and then another n plus 1, I think. Am I right? Oh, the 2 is not there. 2 is not there. Okay, I have an n cubed finally, but this is getting more complicated than I thought it would. But I think it is an n cubed, because I have an n squared here. This is an n cubed minus n squared plus n squared, sorry, minus n squared. So it is an n cubed. Yeah, it is an n cubed, okay. So the sum of the cubes is the square of the sum of the numbers. Okay, so that's what we conclude. And that is it. I hope that I took 10 minutes, because they told me that I need to take only 10 minutes. So I don't know if I exceeded the time or not. Anyway, that's it. Anything that you want to put forward?
Because sigma n, the triangle of
because, okay, so if you sum all of these, all of them you get a 2n plus 1, right? So we have as many 2n plus 1s as we have numbers on this triangle. So how many numbers do we have on the triangle? I have 1 plus 2 plus 3 plus 4. So I have sigma n numbers on that triangle. Right? There are other weird ways of summing up numbers, by the way. This is not the only way. There are lots of ways. One of them uses integration, for example. It's very weird. I once presented it at one of the MMS talks as well. Incidentally, today I wanted to come because I really love this society, the MMS, and even though I was very busy, I mean, between noon and 1 p.m. I had a lecture, but I tried to come because it's nice to see that the MMS is kind of, I don't know how to say it, but it's been a bit dormant, and now it's having a bit of a revival, and I'm really glad that that's happening, because I have, I won't say close ties with the MMS, but I was always a supporter of this. So you have me as a supporter again. Okay, so thank you for reviving this.